So in this video, we're going to talk about how to use symmetry to simplify the evaluation of a definite integral. And in pre-calculus, there were two types of symmetry that you had to deal with. You had to deal with even symmetry, and you had to deal with functions that had odd symmetry. And your test for even symmetry was you needed to check to see if you were looking for even symmetry. So even symmetry, you needed to check to see if f of the opposite of x was the same as f of x. So for example, a function like f of x equals x squared plus 1, which is the function that's shown right here. We could test it for even symmetry by putting the opposite of x into the function. So then everywhere we see an x, we put in the opposite of x. And we square everything out in this case, and so we see what we get. And if the function that we have here is the function that we started with, we say, hey, this is just the same as f of x, and indeed f of the opposite of x is the same as f of x. And if you have even symmetry, if you're integrating over a closed interval from opposite of a to a, so in this case, opposite of a to a, if you're integrating over the closed interval from the opposite of a of a function f of x that has even symmetry, what you want to notice is that the area under the curve between negative a and 0, the area under the curve between negative a and 0, is the same as the area between 0 and a under the curve. It's just reflected. So the area, this area is just reflected on top of this area. So functions with even symmetry, the hallmark of them was that they were a function of themselves in the x-axis. So this area under the curve can be reflected onto this area under the curve. And the bottom line is that this means we can rewrite this integral and just say, instead of calculating the integral from negative a to a, just calculate the integral from 0 to a. Calculate the integral from 0 to a, and that's going to give you this area under the curve right here of your even function dx, and then double it. And you'll have the same area as if you had integrated from negative a, or the opposite of a to a of your even function f of x. And this isn't advantageous because when we find our antiderivative, of f, and we do f of a minus f of 0, in general, evaluating the function when the input is 0 is going to be an easy calculation to make, much easier than having to evaluate it at the opposite of a. So this is a common technique for simplifying the calculation of a definite integral, is to identify, do you have even symmetry over your closed interval? If you do, use it to simplify the definite integral calculation. The other symmetry to look for is odd symmetry. And the hallmark of odd symmetry, when you tested for it in pre-calculus, you check to see if f of the opposite of x was the same as the opposite of f of x. So for example, this function right here is the function f of x equals x cubed minus x. And to test it for odd symmetry, I would simply insert the opposite of x into the function. So everywhere I see an x in the original function, I replace it with the opposite of x. And then we simplify, so when I raise a negative to a third power, I still have a negative. It'll be negative x cubed. A double negation will be plus x. And then I'm checking to see if f of the opposite of x is the opposite of f of x. So I want to factor out an opposite or negative sign. So I factor it out. And then I say, what's left behind? So I use the distributive property to factor that out. And then I look and I say, is this the original function f of x? And it is. So I replace it with f of x, and I see that f of the opposite of x is indeed the opposite of f of x. So this function has odd symmetry. And so the nice thing about odd symmetry is if you're integrating over a closed interval from the opposite of a to a, Odd symmetry will guarantee that there's exactly the same amount of positive area as there is negative area. In fact, this area will be the same as this area rotated by 180 degrees about the origin, or this area reflected through the origin. So we get a positive area here and the negative area whose magnitude or size is the same, and they cancel each other. So if we have odd symmetry, then the integral from the opposite of a to a of a function with odd symmetry is just going to add up to 0. The area under the curve, the net change, because of the odd symmetry of the function, will be 0, as the negative area completely cancels and exactly cancels the positive area under the curve.